Hello, I'm Professor Watson, and this is the recap for the class we've just done on cross-validation, feature engineering, and overfitting. So in this class, we started out by, I'm actually going to break this into two videos. The first one of these videos is kind of the recap of the class. The second one of these videos is because in this class, we introduced three new models. And I just want to talk very briefly about how those new models, which are all class, kind of fit into the work that we've been doing. In this class, they were just kind of a black box. You just learn the vocabulary word for them, but they kind of deserve their own little introduction, and we'll talk more about each of them later in the class. We often use them in other assignments and other free class works, but here I just wanted to kind of get them into its scope by talking about them in this area. So we started out this class by reviewing some of the things we've been talking about in class so far. And one of the things I pointed out in the class is that we've been a lot of the kind of statistical learning objectives that, you'd think were kind of core of a machine learning class were not present in our classes so far. We've been spending much more time focused on things like optimization, things like linear algebra, things like doing regression equations, learning algorithms, stuff like that. We haven't really talked about like probability, distributions, confidence intervals, sampling, things like that, things that you think are really core. One of the points I made about this, and I think actually David in the class brought this up, was that, if you're building a class and you start with the idea of probability, you have no idea what machine learning model to put first. But if you start with the idea of regression, you kind of know which machine learning model to put first. You put linear and logistic regressions first. And so that's what I did. So I saved these probability things till now, both so that I could introduce some models and keep kind of the scope of class simpler as we went along, but also so that in these, when we do introduce probabilities, I wanted you to have a concrete example of this. This is the concrete example of this that we built in class, and that I think is really useful in understanding some stuff about how what we're doing moving forward is this model turns. So one of the classic techniques that you need to do when you're doing machine learning is you need to do training test splits. You need to do cross-validation on your models. And what this comes out of a kind of statistical framework where you're thinking, okay, so I'm going to choose a model, I'm going to train it on some data, and then I'm going to measure its performance. But hey, what if you happen to sample a subset of data that happens to just do really well or really badly on these performance metrics by chance? That's certainly a thing that could happen, right? You could construct a model, and one of the examples I gave classes, imagine you construct a model that's just trying to guess on a number 1 through 10 from a uniform, being trained in a uniform distribution of the numbers 1 through 10, right? Well, if I ask it to guess 10, I've trained such a model, with the maximum likelihood estimator will probably guess about a mean. And so you'll get a number of about 5.5, right? Is the number that the model will guess. But if I then test that model on 10, it makes a big error. If I test that model on 5, it makes a small error. And so how do I know that I've actually trained my model that this is an appropriate model to train in this data? If, I can get big variation in the performance based just on what I happen to sample. And so the kind of principled approach for this is to do something like cross-validation. And this is something that's really going to undergird a lot of our models going forward. One of the reasons that I was able to introduce so many models is if you have this kind of test and training harness built, and I encourage everyone to kind of build an example of this for themselves in Python, you can kind of drop in different models and just test them on your data. And now a model becomes no more, trying out a new model is no more difficult or easy than trying out a new data set, than trying out a new metric for measuring. All kinds of things become really easy with this framework. So this is the general framework that we outlined in class. We talked about how, you select a model, you initialize its parameters, you now have an untrained model. You'd like to train it, but before you can fit the parameters of that model, you need some data. So you import data, you do some pre-processing on it. We use dimensionality reduction like PCA on the data in this class. And then we also use one-hot encoding, which is a way of taking categories and mapping them to a vector where you have one in the cell of that vector. Each category gets one rank, essentially one row on that vector. And the first category has a 1. If the first category is present, there's a 1 in the first vector, and the rest are zeros. If there's a second category is present, it's 1 in the second and zeros everywhere else. And so we did some one-hot encoding, we did some PCA, and then we started doing train test splits in the data. And I actually had a student put in a really nice infographic for this that I will show in a second here. But what that train test splitting does is it's splitting up your data into different segments, right? Using some of the training and test data to train the model to fit the parameters so that the model parameters can predict the target data, the Y data from the X data from the sample data, right? And then you save some of this back so that you can test the model after the fact. So you can test it on data that is out of sample, that it wasn't trained on, right? You do that by taking the test X data and using it, putting it into the trained model, getting a set of predictions, which are its predicted Ys, and then comparing them to the residuals you've been computing the residuals, comparing these predictions to the test data, the original test Ys. The errors you compute then are a measure of your performance, of your model's performance, and you freely visualize that in a number of different ways. So we've talked about every element of this except for this cross-validation set. What the cross-validation set is, it wants to deal with that fact of, you're making this, you're subsampling your data to make this train test split. What if you subsample in a way that either dramatically increases or decreases the performance of your model? And so there are a couple of things you can do. One of the ones that I thought had this really nice infographic is you can take your data, you can split it broadly into a set of data that you're going to use to train models and a set of data that you're going to use to test or validate your models at the end. Again, vocabulary varies a lot here. You'll notice in this one, the training and test data are kind of used in two ways. So we take our training data and we break it into 5 segments. We fit the model on 4 of those segments and test it on the one left out segment. This is cross-validation. In the second split, we do it again, do it again, do it again, do it again. Each time we test the model on a different subsegment of the data until we've tested the model on all 5 subsegments of the data, right? And in so doing, we've trained models to make predictions that we validated our predictions on subsets of the model that they were trained on every single time. But now we've also validated the model across all 5 of those. Now, at this point, there are a couple of things you can do. So the first thing you could do is you could train a single model in a approach called fine tuning, where you train a single model using all 5 of these splits, right? The model should get progressively better. You might use a process like simulated annealing on the model so that the model resets its weights a lot, takes big adjustments in the beginning and small adjustments at the end. We'll talk about that some more later in the semester. After doing this fine tuning, you might test it on your held back test set of data, and that's the value that you report at the end. Another approach is actually to use an ensemble approach, where you actually train 5 different models. So you create 5 untrained models, you train and test each model on one subset of this data, and then you have all 5 models make predictions about the test data. And what you report is either the mean, if you're doing something like regression, where you're trying to get out a single value, or you have the models vote. So in this data set, we were working with the Pokemon data. So we're actually trying to predict the type of a Pokemon from the picture of the Pokemon. Obviously there are some things like color in there that might be informative, right? If the Pokemon is grass type, it's more likely to be green. And so in this case, what you do is you train 5 different models or 5 different subsets of your data. You'd have them all make predictions. And then you'd take the models that agreed on a prediction. So if all the models agree, then all the models say this is a grass type Pokemon. You say, okay, this is probably a grass type Pokemon based on this picture. But let's say 3 of the models think it's grass type and 2 of the models think it's poison type. Well, then you go with grass type. Often there are even things you can do, which we'll talk a little bit later in reporting out your metrics, where you do something like you report out the top K. So you report out the top 5 categories that the model thinks it is, and you give yourself partial credit if any of the right options are on that list. So I think this is a great way to visualize the procedure that's going down when you're doing this cross-validation. And it's really important because it protects your model from getting weird samples and getting weird performance. It also makes your output a lot more plausibly probabilistic than if you were just doing fitting a single model and testing it on it. It is reasonable to believe that your model might do better or worse given different random initial parameters or given slightly different data sets. And so it's somewhat misleading to report a single accuracy value or a single, sum squared errors or something out, a single metric at the end, because that's sort of saying that the output of this model is a point. It's a single metric. And as we're introducing some of these new learning objectives, I want us to start thinking more in this class about probabilities and distributions. And so I want our outputs to also be probabilities, also be distributions. You can look at, if you fit 5 different models and you have them all test on the output, you can get a range of accuracies. And your distribution, you should expect your actual performance to be drawn from that distribution of performance. You shouldn't be looking at things as trying to produce a single answer. You should be trying to produce a range of answers, a cone of uncertainty around what you think is the best estimate. And something like cross validation actually does a much better job of doing that. So that was the bulk of what we covered in class. We created this model harness in which we did a bunch of feature engineering to get our data pre-processed and segmented into trading and test splits. Second, we wanted to defend against overfitting by doing cross-validation. So we split our models into multiple tranches and we did cross-validation sets. And everybody in the class went home with some code that would help them do that. All right. We also tried out a couple of different models in this to see if there was any variation among models. Because again, we should, be thinking in terms of probability distributions on our outputs. We want to have ranges of different outputs, ranges of different, distribution of different performances. And one of the major components in those different performances is the different models that we use. So I'm going to do another short video that follows this one that just gives a very 30,000 feet quick introduction to the three models that we covered in class today and puts them in context with the other classifier that we've been working with so far, which was the logistic regression classifier that we started out with. So I'll see you in the next video for that. In the meantime, if you are following along, try to make sure that you have this model pipeline set up and ready to go for our future workshops, because we'll often interrogate a model by just dropping it into something like this, cross-validate, telling you to perform. All right, I'll see you in the next video.